Okay, gonna try something different today. I'm not at school, so let's see how this works. So, in middle school, you talk about the atom, but you never really go into detail. And in high school, you tend to go into some deeper detail. In chemistry, you go into a lot more detail than we are going to go into, but still, we're diving kind of deep, okay? So we're gonna talk about the structure of the atom and all the subatomic particles that make up every atom, right? Subatomic means they're smaller than the atom. Subatomic means they're smaller than the atom. And in the case of the average everyday atom, which there's no other thing, nothing else, there are three parts of it that if you wanted to make an atom, you'd have to have these three parts. One is called the proton. Now, if you'll notice, the protons are found in the nucleus. So this is the nucleus of the atom where the red dots and the blue dots, and you'll see the red ones have a plus sign, okay? So found in the nucleus, and it has a charge of 1 positive. Now, don't get all confused in that. All that is telling you is that it has a positive electrical charge, and there's only one per proton. Okay, so this would be your positive electrical charge. You know, think of electricity. If you've ever been shocked, that's negative electrical charge, but this is a positive electrical charge, and the protons contain 1. Okay, kind of important, only 1. And then every atom has at least 1 proton. Matter of fact, this is how we identify the element by the number of protons it has. Okay, so every atom has at least 1 proton, has 1 positive charge. And then if I kick it up a notch for you guys, the scientists give it a weight of 1 atomic mass unit. So our brains like to categorize, weigh, number, quantify. This is how we do it. 1 AMU, 1 atomic mass unit. Okay, keep that in mind. Now, the next one is the electron. The electron, the word electron is a Greek word that means amber. And if you've ever seen a picture of a fossilized insect who's been stuck in amber for millions of years, that amber is something that pine trees produce, and it's notorious for generating static electricity. So you could actually rub the amber and get a static electrical charge out of it. And so they call the electron, they named it after that, okay? Now, this little green particle, that's your electron. It has a negative electrical charge. Now, we know what that feels like if you've ever touched the doorknob, you got snapped, okay? That's an electrical charge. If you stuck your finger in a light socket like my friend Nick, you felt that, right? And so you'll notice that it's found orbiting the nucleus. So here it is going around these dots here, this cluster in the nucleus, and that's all they do. They stay out. They move really, really fast. Now, if they were to stop moving, they would crash in and the universe would end, but they move so fast around that they can never actually touch, even though they're attracted here. Because negative is always attracted to positive, negative is always attracted to positive, but they move so fast that they can never actually touch, okay? So it has 1 electrical charge, very important. Now, see here it says 2,000 times smaller than a proton. Wow, so think about this. If a proton weighs 2,000 pounds, an electron that's zooming around here only weighs 1 pound. And so kind of a cool little tidbit you could tell at a party one day. Okay, so you had your proton, positive electrical charge, electron, negative electrical charge, and I put them together for a reason. Now, the third particle, neutrons. If a country doesn't take sides in a war, it's called neutral. Well, neutrons, you'll notice it doesn't have a positive electrical charge, it doesn't have a negative electrical charge, positive or negative, and it's neutral. It just kind of sits there. I think, to me, it just adds weight. I don't know any other part about it, that it just adds weight. And it's found in the nucleus, so you can see that right there with the protons, there's the neutrons, right? No electrical charge, and they're about the same size as a proton. Actually, they're just a touch bigger, and so it would be like 1.1 AMU. So they have mass, they're adding weight, adding some oomph, and so keep that in mind. So that's a neutron. Proton, electron, neutron. Now, numbers to know. Numbers to know. Now, if you had your periodic table, you would see if you would look at the element carbon, it would be set up something like this in its tile on the periodic table. And the atomic number is up here, and carbon has 6, the atomic number, and then carbon is the chemical symbol. It would be in the middle. It's a big letter, capital letter, and down here below you have the mass number, which we're going to get to in a minute. Okay, the atomic number is kind of cool, because if you look up the atomic number, it's always going to tell you that that is the number of protons in the nucleus of that atom. Okay, and so in the case of carbon, you'll see that it has an atomic number of 6, so it has 6 protons. 6 protons. So if I write that over here, it has 6 protons. Automatically we know that. It's very unique to each element. If this is 1 up here, that would be hydrogen. See, like right here, so hydrogen has 1 proton, that makes it hydrogen. It's like my fingerprint is different from your fingerprint. It's an identifier for elements. And then 118 protons, that's the last element on the periodic table. So this is the first one, this is the last one. Uninoxtium is really big, it's really heavy. This only has 1 proton, so it's 1 AMU. This is 118 AMU, just in protons alone. And it's going to increase the number. If you look at a periodic table, you know, like we read from left to right, you'll notice that there's 1, that's hydrogen. If you go all the way to the other side, that's 2, helium. Helium has 2 protons. And then you just keep going, and it keeps getting bigger and bigger and bigger and bigger. Okay? And again, if you have questions, write it down or raise your hand. Now, the next number is called the mass number. The mass number is simply this number right here. The mass number is the number of protons and number of neutrons that you can find in the nucleus. The number of protons and the number of neutrons in the nucleus. And so this rule here states that the number of neutrons, easy to find. You just take your mass number and minus, and anybody can do this, a first grader could do this, mass number minus atomic number gives you the number of neutrons. Well, how does that work? Okay, if I have 6 protons, but I have a mass of number of 12, if I take 12 minus 6, that equals 6. Well, that number 6 is the number of neutrons that we're going to find. And so all we can do is take the atomic number and subtract it from the mass number, and it always gives us the number of neutrons. Okay? So remember that rule, number of neutrons is equal to the mass number minus the atomic number. Okay, next term, isotopes. Like human beings, there's different forms of human beings. Different forms of human beings. You are different from me, I am different from you, we're different from each other, but we're still human beings. Think about isotopes. Isotopes are different forms of the same element. Now, down here I say it's the same element that has different number of neutrons. Okay, I'm getting a little more specific, but to introduce you to the topic, it's different forms of the same element. Well, here we have hydrogen. How do I know? Well, I have a P, 1 proton, 1 proton, 1 proton. That H there tells me that's hydrogen, hydrogen, hydrogen. But you'll see they're different forms. And the only way they're different is the number of neutrons. See down here it says the number of neutrons, different number of neutrons. So this one here, this is the one you find on the chart. This is called protium. Okay, it has 1 proton, 1 electron, no neutrons. That's just the way it is. Okay, deuterium, deuce, Deu means 2, and so it has 2 particles in the nucleus. It has 1 proton, 1 neutron, and still only has an electron. Now remember, all you did was you added a neutron, but you're not adding a proton. If you added a proton, it would become helium. And we move down, we got an even heavier form of hydrogen called tritium. Tri means 3. And so you got your proton, and then you add 2 neutrons. That gives you the mass number of 3. So down here is the mass number of 1, mass number of 2, mass number of 3, and then your atomic number stays the same. That tells you, oh, hydrogen, hydrogen, hydrogen. And down here it just tells you how many. So if you take 3 minus 1, that equals 2. 2 what? 2 neutrons. So here they are, 2 neutrons. Okay, that is an isotope. This is found naturally in the oceans and all water. You drink heavier water, it doesn't hurt you. We use these two especially in making nuclear weapons, nuclear fuel. So they're kind of important. So that's your introduction to isotopes. Okay, now atomic theory. I'm not real big into history, but you should kind of know what we're looking at. So in the early 1900s, a guy named Niels Bohr, he had an atomic model, and we kind of use in education, we use his model. You'll see it here. This is his atomic model. You need to know this for the test so you know what you're looking at. Okay, and it always has a positive nucleus because really what's in there? You know, you got positive protons, you have neutrons. Neutrons don't have a charge, so it's always going to be a positive nucleus, positive electrically charged nucleus, and then the negative electrons are going to be zooming around it. Okay, now you're going to notice that there's 1, 2, 3 shells, orbits, shells or orbits. The first shell is going to hold 2, and then in this case it's going to be 1, 2, 3, 4, 5, 6, 7, 8, and this one holds 8, and then you got this one lone one floating around out here. Okay, the first orbit only has enough energy to hold 2 electrons. So this is a lowest energy orbit. Okay, think of it as a small shelf that only has enough room for 2 electrons. So it's a low energy, can only hold 2. And then the higher you go, the more energy is available and it can hold more electrons. So if you made a guess, this third orbit, it's going to be able to hold more electrons than the second orbit. Okay, so this is kind of what we use in education, even though this is not what an atom really looks like, but it helps us to understand. Now, electrons move. Okay, and Professor Bohr figured it out. And whenever an electron gains energy, electrons are going to move up. They're moving up. But whenever they lose energy, the electrons move down. So they gain energy, the electrons move up, and magic happens. And when they drop back down, they lose energy. And so the proof that electrons move is when an atom absorbs energy, the electrons move to a higher level. Okay, so you could add heat, that might do it. Okay, and when they move down, they are going to release light. So if you ever watched, July 4th celebrations, the different colors are from different elements that are kind of dictated by how much energy they transfer, I guess would be a good way. Barium is green, strontium, it makes the red in your fireworks. And so they don't have the same energy levels, and they are going to give different colors of light as the electrons move around. So we know that they move. Okay, when they move down, they release light. When they move up, maybe some heat. And you can hear some sound too from the chemical reaction. Now, here's the current model of the atom. Now, look at that windmill. And you notice it's moving, it's blowing, you can't see the individual blades. Moving so fast, you just can't see it. That's what we found out an atom looks like. An atom is gonna look like that. It's gonna be very fuzzy. You won't be able to even see the nucleus. And what's cool about this, and it blew my mind, is that an atom could be there at any one time. It could be there, it could be there. They move so fast that you can't really predict where they are at. They don't behave like we originally thought. So they could be here or here. And so they call it the electron cloud because it's kind of fuzzy and you can't really tell. And again, this is the current one. So make sure you know the difference, what it looks like. Okay, now, next step. Let me see what this says. Every 10 minutes, place a dot with the tip. Okay. Don't know what that was when I wrote it down. Okay, so atomic orbitals. So here's the nucleus, here's the positive charge, and then you'll notice that this first shell, they call it the K shell, holds 2, then the L shell holds 8, the M shell holds 18, and 32, and you'll notice that it keeps getting more energetic. And so what would be kind of cool for you to know is that the first shell holds 2, 8, 18, 32. 2, 8, 18, 32. 2, 8, 18, 32. Okay? And then each orbital has to hold at, I can't remember what I did there. So energy level 1, number of orbitals, 2 electrons. Oh, this is just it's showing you the different orbitals. It says each orbital holds 2 electrons. So in this one here, this 8, there's 4 orbitals that hold 2 electrons. So that means that total shell 8 holds 8 electrons. Same thing, there's 9 orbitals in number 3, which is the M, and then that's 18, 16 in the 4. So you can think of it as like an orbital has shells holding 2, and then altogether it holds 32. But the big thing I'd want you to remember is that the number of electrons in that shell. So the first shell holds 2, second shell holds 8, 3 holds 18, 4 holds 32. Now remember, electrons move. Last thing, electrons move. And when there is no energy, they're involved, they're just being electrons, they're in a ground state. This is them in their lowest level. This is their normal state. They're extremely stable. Okay? But when electrons move to a higher level, they become unstable. So this could actually move up to a higher energy level whenever energy is added, and it becomes unstable, it becomes excited. Okay, and remember, when it returns back to the ground state, that electron will drop back down and it will probably release a little light. And so if any electrons move up to a higher level, a higher energy level, they become unstable. And when they move back, they're now more stable and they're in a ground state.